is going to be a good day. If you can bear with me, I'm warning you, we're probably going to go to the bell. Okay? We're probably going to go to the bell with notes. However, on Monday, we get a day to just work on a worksheet. Okay? To just figure some things out. So we're going to take some notes, probably to the bell. You're going to have a homework assignment over the weekend, but then on Monday, we're going to get a chance to put everything that we've learned together and just do some problems together. Okay? So I will reward you with a lot of work time Monday if you can bear with me through today. Okay, first thing I want to talk about is the fundamental theorem of algebra. Okay? Now, this is something that you've kind of thought about already, especially when we did those graphing packets. But now that we have introduced complex zeros, we need to talk about our zeros in general. Okay? Is it possible for a graph or a function, we're going to say polynomial, is it possible for a polynomial to have an imaginary zero? It is. You guys remember your quadratics chapter. If we have a parabola opening up and the vertex is above the x-axis, it never crosses the x-axis. We could have an imaginary zero. Okay, so what the fundamental theorem of algebra says is that if we have a polynomial, then there is at least one zero that is in the complex number system. Okay, basically if we have a polynomial, we will find a zero. That is what it says. It seems trivial, but it's actually a very complex thing to prove. One of my math classes in college was proving this theorem. Well, a part of it, not like all of it. Okay, let's be more specific. If we have a polynomial of n degree, how many zeros will we find? How many? N. That's something we talked about last week, right? So specifically, there will be n zeros. Now, some of them may repeat, right? We could have some multiplicity, but there will be n zeros. Now, we've kind of already talked about linear factors when we did the 2.3 homework assignment. Okay, they made you do some linear factorization. Linear factors mean x minus a zero, x minus a zero, x minus a zero. So if there are n zeros, how many linear factors are we going to have? How many? N. Do we need to do some jumping jacks so I can get you awake so you can participate? Don't make me do that. I will. Okay? If we have an nth degree polynomial, we will have n zeros, which means we'll have n factors. Okay? It is your job to be able to give me zeros, and it is your job to be able to write them as linear factors. Now, going the other way, I also want you to be able to write a polynomial. Okay? So let's say we have zeros. Please write these zeros down. 1, negative 2, 3i, and negative 3i. Okay? If these are your zeros, to write linear factors, all we have to do is write x minus the 0, just like you did on that second graphing packet a week ago today. Okay, last Friday, we did all of that multiplication. Now, I'm not going to multiply these out, but if these are our zeros, then our linear factors would be x minus the 0, x minus the 0, minus the 0 and x minus the 0. Okay. We're not going to take the time to multiply this out, but let's talk about the best strategy to do that. What would be a good first step if we were to multiply this out? Okay, multiplying these two together would be a good first step. You do not want to multiply a factor with imaginary number with a factor that doesn't have one. Multiply these conjugates together first, okay? Then that will help you the rest of the way. Probably what I would do is I would multiply these two together. I would multiply these two together, and then I would take those two products and multiply them together, just to save you some room. All right, now, Caleb, you had a thought. What was that thought? Okay, Caleb is saying eyes come in pairs. Do you remember something that sounds like that? Maybe, maybe not. If you don't remember, here's your reminder. If you have a complex 0, then you will also have its conjugate as a 0. Complex conjugates come in pairs, or complex zeros come in pairs. I'll give you a moment to write this down, and then we can talk about it a little bit further. You don't have to write every single word down. You can abbreviate, you can reword to be your words, okay? But if a plus bi is a 0, a minus bi is a 0. Okay, so our zeros, if we have complex zeros that have an imaginary number, okay, they're going to come in conjugate pairs. Let's think about some things that we can do with that, all right? If I say we have a third degree polynomial, imagine what a third degree polynomial looks like. Is it possible for us to have a third degree polynomial that does not cross the x-axis? Eli, why not? I heard you say that. Well, how do you know that?
Because the paragraph does that.
Okay. That's a good thought. What else have we talked about in this chapter that we could lean on for help in explaining this?
It adds an odd number of zeros, and the complex zeros come in pairs, and then there has to be a zero that's not complex.
Okay, if complex zeros come in pairs, 3 is an odd number. We can't have 3 complex zeros. Okay, which means we could have 2, but at least 1 has to be real. Okay, a real zero means we're crossing the x-axis. Okay, what is another thing in this chapter that we could use as an explanation? Kind of going back to what Eli said. Well, I know you basically said I know it's going to look like this, right? What in this chapter tells us that it's going to look like this? Okay, but we have a leading coefficient test, right? We know that an odd function is going to have opposite behavior, okay? That's another explanation if you want that, okay? If it has opposite behavior, it's going to have to cross the x-axis, okay? Now, what else can we do with this? I am giving you that 1 plus 3i is a 0 of this function. Go ahead and write this function down, and that our 0 is 1 plus 3i. All right. I want to find all the zeros. Liam, how many are there going to be? 4. We have a 4th degree polynomial. We have 1. What? We have 2. What is the other one? 1 minus 3i is also a 0 because they come in conjugate pairs. Awesome. How do we find the other 2?
You can multiply the conjugates together and divide that out.
Okay, Nick is saying we can multiply the conjugates together and then divide them out. Does that seem like a reasonable offer? Any other ideas? What's your other idea? What? You like Nick's idea. Okay. Now, the only thing I'm going to change about Nick's idea is we can't just multiply the numbers together. We're going to have to multiply the factors together. Okay? So if 1 plus 3i and 1 minus 3i are zeros, then we know that x minus 1 plus 3i and x minus 1 minus 3i are factors that should divide evenly into the polynomial. Okay. So now we get to multiply this out. Okay. Everything in this has to be multiplied to everything in this. So let's do it. X times x, x times negative 1, and x times 3i. You guys okay over there? Okay. Negative 1 gets multiplied to all three. So negative 1 times x. Negative 1 times negative 1, and negative 1 times 3i. Negative 3i gets multiplied to everything. So negative 3i times x. Negative 3i times negative 1. Negative 3i times positive 3i would be negative 9i squared. Positive 9. Okay? Now, the nice thing about multiplying when we have conjugates, we have terms that will cancel out. So we have x squared minus 2x plus 10. All right, well that's cool. What are we going to do with that?
No, we're going to have to divide.
We are going to have to divide it out. I don't know. Okay. We are going to have to divide this out. And what is our only option for division? Long division. All right. So we have x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60, and we are dividing by x squared minus 2x plus 10. Now some of you are moaning and groaning. However, if this is a problem that you missed on the quiz, here is some practice for you as you go into the weekend to make your corrections. Okay? Okay. X squared times what is x to the fourth? X squared. We're going to put it in that column. Remember to multiply the divisor times that number. We are subtracting. My strategy is just to change all the signs so that we can remember the subtraction. Okay, so what we're left with is negative x cubed minus 4x squared. Bring down the next term to continue the division plus 2x. Okay, so now what is x? X squared times what is negative x cubed? Negative x. Let's take the divisor times negative x. Okay. We are subtracting, so change the signs. When we combine those terms, we have negative 6x squared plus 12x. Drop down our last term, minus 6. All right, last time around, x squared times what is negative 6x squared? Negative 6. We should get a remainder of 0 because we know that we got x squared minus 2x plus 10 with zeros. Okay, so it should divide evenly. All right, so let's talk about what we know. We know that x minus 3 plus I times x minus 3 minus I. When we divided those out, left over we got x squared minus x minus 6. So that is how we could write our polynomial, right? Now, x squared minus x minus 6. Is that something we can factor? Callie, what does it factor to?
X minus 3 plus 7.
Okay, so what we have zeros of 3 plus or minus I. I am perfectly fine with you writing zeros that way. Oh, did I write those completely wrong? Thank you, Marissa. It's 1 and then 3i? Okay, so 1, like that. Thank you. Okay, so our zeros are 1 plus or minus 3i. I am okay with you writing the zeros like this. You can write them separately, but when they come in conjugate pairs like that, you're welcome to write the zeros in this manner. And then we have zeros of 3 and negative 2. Okay, let's talk about what your other option would be. Your other option would be to take those imaginary zeros, and you could have done synthetic division twice. And then you would be left with the x squared minus x minus 6. Okay, so you're going to have a couple problems like this in your homework. You can do either method. This is the method we did in class. If you'd like to do synthetic division twice with complex zeros, go for it. See how it goes for you. If you like this method better, stick with it. All right, let's talk about one of my favorite things in mathematics, the rational zeros test. Remember the guessing and checking we were talking about earlier, or a few days ago? Here it is. Okay, let's first of all talk about why the rational zeros test. Okay, are there polynomials that you are not able to factor? Yes. especially if I give you one with like 5 terms, nothing in common. How the heck do you factor that, right? Okay, so we need to be able to find zeros of a function. Now, we could just start plugging in 1, 2, 1/2, 3/4, 3/5. Does that sound enjoyable? No, we have an infinite number of possibilities, okay? Maybe we could narrow it down to a smaller pool of numbers to try to test for zeros. Would that be better? I think it would be better. Okay, the rational zeros test, okay? If a polynomial has a rational zero, they are going to be in the following form. Okay? Now, I'm going to undo my screen shade, and you can write down what you need to, and then we'll talk about it. Okay? This is something that you went through in Algebra 2. Okay? You've been introduced to this. All right? Okay, the rational zero is of the form p divided by q, where p and q have no common factors. P is the factor of the constant term, and q is the factor of the leading coefficient. So just write that down, and then we'll talk more. Okay, this is going to help us create a pool of numbers. All right, instead of just any number, just throw in there. This is going to help us create a pool of numbers. We're going to list all of the factors of the constant term, so the term on the end of our polynomial. We're going to list the factors of our leading coefficient. We're going to create a list of numbers for us to test to see whether they divide evenly or not. Okay, this does make more sense when we do an example. So let's go ahead and do that. Please write down this polynomial. It's not too crazy of a polynomial. Now I will say the rational zeros test helps us find zeros when we cannot factor. If you can factor a polynomial, by all means factor it. It's going to take less time. The rational zeros test could take a little bit of time because we are plugging in numbers to see if they work, and they might not work the first time around. Okay, so it's essentially going to be guessing and checking. But we have a methodical way of guessing and checking. So our possible zeros are in this form. In our numerator, we take factors of the constant term. What are factors of 3? 1 and 3. Technically plus or minus 1, because it could be -1 times -3. Do you agree? Okay. Plus or minus 1, plus or minus 3. Okay. Over. What are factors of the leading coefficient? 1 and 2. So our possible zeros, I want you to list them out. 1 divided by 1, 1 divided by 2, 3 divided by 1, and 3 divided by 2. Now, this doesn't mean that all of our zeros are rational, but if there are any that are rational, they're going to be one of those 8 numbers up there. So here's where it gets exciting. We get a guess and check, right? Here's where synthetic division and a pencil is your friend. If we have a zero, this is what we're working for right there. If you don't get a zero, erase, cross that number out. Okay? We have 8 numbers to try. What do you want to try first?
1.
1 is always a good number to try first. It's easy, right? So let's try 1. Bring down the 2. 2 times 1 is 2. 5. 5 times 1 is 5. What happened, Eli?
Yes.
That was great. That was a great guess. I would only start with 1 and -1 because those are the easiest to multiply through. They take less time. Okay? All right. So we tested 1. We got 0. Woohoo! We got a 0. Okay? Now, it will not work like that every time. Sometimes you'll go through synthetic division 3, 4, even 5 times before you find one that works. Okay? So let's talk about what we are left with. We are left with x minus 1 times 2x squared plus 5x minus 3. Is that something that we can factor? Hopefully. I will tell you, there could be times where you get down to a quadratic and you can't not factor it. And then you would have to rely on the quadratic formula. Okay? You could see that, so don't panic. All right? But it is easier if we can factor, so let's try that. Okay? To get 2x squared, I know I need a 2x and an x. To get minus 3, I need a 1 and a 3. Any advice on where to put those? Chris, what do you think?
Minus 1 plus 3.
So then we get 6x and minus x. Okay, good. What I have written right here, this is the product of linear factors. Okay, so if you are asked for linear factors, that would be your answer. But if you are asked for zeros, you would get 1, 1/2, and -3. Were 1/2 and -3 in our list of possible zeros? They were. So we could have started with 1/2 and gotten there. Okay. Questions? Do you guys remember guessing and checking and being patient? Now I will say, if you have a 4th degree polynomial, use a 0, and then just like we did when we were verifying factors, use what's left over to continue. Okay? Now, there are 5 minutes left. I think we're going to get through what we need to get through. There is something that can help you decide which numbers to start choosing from that list of 8 numbers, or 10 numbers, or 12, or however many. It's called Descartes' rule of signs. And I was told by your Algebra 2 teachers this is something that you have talked about before. So I'm going to give you a couple minutes to write down, write Descartes' rule of signs. Don't write this first sentence right here. We're going to save some time. We have 2 pieces to write down. This is the first piece. So Descartes' rule of signs is going to tell you how many positive real zeros you could have and how many negative real zeros you could have. All right? So if using Descartes' rule of signs, you get that there are no positive real zeros, don't try any positive numbers in synthetic division. Okay? Now, it says the number of positive real zeros is equal to the number of variations in sign or less than by any even integer. So by sign variation, it means this. Like this goes from positive to positive, that does not vary. But going from positive to a negative term, that's a variation. And negative to positive, that's a variation. Okay? So this one has two sign variations. Okay? Now, we could have we could have imaginary zeros. So if there are two sign variations, there could be two positive real zeros, or there could be zero, because that's two less. If you get three sign changes, there could be three positive real zeros, or there could be one, because there could be two imaginary. All right? And then you have the same rule for negative real zero, except you are looking for the sign variations for f of negative x. Okay, now I am not able to show you an example right now because the bell's about to ring. So I will tell you the first three problems from your homework assignment deal with Descartes' rule of signs. You are welcome to try them, but if you don't try them, it won't count against you. I will go over an example Monday at the beginning of class. So if you'd like to try it, because you kind of remember how to do it, go for it. Otherwise, do the rest of the homework and save it's like 90 something, I think. 90, 91, 93, those are Descartes' rules. Okay? So you could save those if you wanted to see an example first. Okay? So book homework I'll look at on Monday. Your quiz corrections are due Tuesday. My advice, do them over the weekend, and what you can't do, you have Monday to figure out. Ask me, ask a friend, whatever. All right? Have a wonderful weekend. Make good choices.